Washington, President Roosevelt sits before a golden key. A touch of finger on key, and across the continent, look. Boulder Dam put into operation. Giant spurts of water bursting into the canyon.
Engineering has been America's traditional solution to its water worries. Dams were built to supply dry areas with water and to catch floodwaters before they had a chance to cause disaster. But as the nation has grown more sophisticated, so have its water problems. Some of our most pristine lakes are being poisoned by acid. This is one of 250 in upper New York State which have already succumbed. Irrigated farmland is being abandoned in some areas where underground water tables have dropped so low that pumping costs make growing crops like corn uneconomical. Many older cities like Boston, with antiquated plumbing systems, are losing millions of gallons a day of expensive treated water through leaks in underground pipes. Groundwater runs through the taps of 40% of our population. Yet every day, wells are being shut down throughout the country because of chemical contamination. Many of the nation's rivers and lakes, which supply the remaining 60% of our drinking water, carry a toxic mix of chemicals. Nationwide, more and more water problems emerge each day. Are we facing a water crisis? Fishing in the clear mountain streams and lakes is what attracts thousands of vacationers who come to the Adirondack region of upper New York State every spring. For the last 100 years, the area's economy has depended on these seasonal visitors. But old-timers began noticing in the 1950s that their catches were dwindling and consisted of large fish only. Something was happening to the lakes. They took on a startling blue clarity as the sunshine penetrated deeper into the water. What made this possible was that there were fewer living creatures to absorb the light. The lakes were dying, and the culprit was acid rain. Acidity is measured in pH. Adirondack rain with a pH of 4 is 40 times more acid than pure rain. Causing this acid rain are sulfur and nitric oxides coming mostly from fossil-fueled power plants in the Midwest. The problem intensified when stacks were raised to reduce local air pollution, as mandated by the Clean Air Act. Tall stacks airmail the pollutants to the northeast on prevailing winds. Particles combine with atmospheric moisture, forming sulfuric and nitric acids or acid rain. As they collide with the Adirondack peaks, the clouds drop their acid into the lakes, which also collect heavy metals leached by the rain from surrounding soil. At Cornell University, acid rain is being studied by gene lichens.
Our data suggests that rain and snow falling over most of the eastern United States is currently acidic. But the effects are seen primarily in the northeastern United States because this is the area that primarily has hard rock geology, granitic type soils and rocks on which the rain and snow are falling. Because of that, the acidity in the rain and snow is not neutralized to the extent that it would be if it fell on limestone or sandstone, shales, or other kinds of rocks which would tend to dissolve or weather more rapidly.
The acid rain falling into the lakes can leach aluminum from the sediment, bringing it up into the water where it poisons the fish. Gradually, the lakes die. But what about streams? Can aquatic life be affected by brief encounters with acid, as happens during spring snowmelt when large quantities of acid are released?
We've taken a natural stream and artificially acidified it, but only to levels that are comparable to incident precipitation. That is, we brought the pH of stream water to 4, which is about our annual average in rain and snow. We were surprised to see how quickly the experimental acidification of the stream could cause changes in the biological components of the stream. Stream invertebrates, for example, were responding to the acidification rather quickly. Within an hour or two, they were responding by coming out of their normal habitat on the bottom sediments into the water column and then being swept downstream by the current.
Loss of food supply may account for the dwindling numbers of fish. The spring snowmelt also coincides with the spawning season. Studies have shown that concentrations of acid have their worst effect on the reproductive cycle of mature fish and the survival of fish eggs and fry. This may be the reason fishermen were not catching any small fish. Could fish be adapted to these new conditions? Researchers at Cornell have conducted experiments with young fish, hoping to increase their acid tolerance. Tanks were stocked with hardy strains of trout from a variety of locations. In some tanks, acid was added gradually, while in others, it was dumped in suddenly. Acidity was kept to the same level as that of the nearby brook during snowmelt. The fish that survived several rounds of this treatment were tagged and dropped into the acid lakes of the Adirondacks. It is too early to know how well they are adapting. A second approach to the problem has been to try to reduce the acidity of the water. Gene Likens.
Currently, lime is being added to acidified lakes. In Canada, in the Adirondack Mountains, in Norway and Sweden, this is a practice that's being applied rather commonly. It's expensive to do that. The effects aren't permanent. It has to be relimed, and there are some side effects.
One can be accumulation of heavy metals in fish, making them inedible.
So it's sort of like taking an aspirin when you've cut your finger off. It might help the pain a little bit, but if you don't do anything else, you eventually might bleed to death.
Vegetation and soils may also be suffering from acid rain, although its effects on them are less obvious in the short run. But the future of agriculture and timberland may be at stake.
In the laboratory, we can show the effects of acid precipitation on plants. One effect is to leach nutrients from the foliage. Another effect is to reduce or thin the cuticle, the outer covering on the leaf surface, thereby possibly opening it up to pathogens or insect pests. There are a variety of effects that we can see in the laboratory. Whether those effects are exactly the same as we would see in the field, we just don't know yet. It's often very difficult to extrapolate what we find in the laboratory to in the field, and this is why we need much more research in this area.
At Whiteface Mountain, a nearly 5,000-foot peak in the Adirondacks, scientists are studying not only the content of the rain, but that of the clouds and fog as well. Ray Falconer of the State University of New York has designed a cloud catcher which collects droplets of moisture passing by the weather station atop the mountain. The filaments vary in thickness to approximate the width of pine needles and small evergreen branches. As moisture moves through, different sized droplets adhere to different width filaments, in much the same way as they would stick to vegetation. The water runs into the lab inside, where an ion chromatograph shows what potential pollutants are being carried in the cloud. This graph recorded a cloud containing high concentrations of fluoride, chloride, nitrates, and sulfates. Rain sometimes forms in the cleaner air of high altitudes where there is less contamination, but as it falls through the clouds of pollutants closer to the ground, it becomes acidic. Weather satellites show pictures of pollutant-carrying clouds with holes where the rain has fallen through. Studies conducted on Whiteface have found clouds with moisture as acid as vinegar. Reducing the pollutants put into the air by power plants is the best way to solve the acid rain problem. The major component of the smoke, sulfur dioxide, can be removed by passing it through a scrubber before it goes up the chimney. Scrubbers are not yet required by law for existing plants burning oil and coal. These spew 20 million tons of sulfur into the air each year. Conversion to coal, encouraged by the new energy policy, will intensify the acid rain problem unless scrubbers are required for all plants or high-sulfur coal is washed to reduce the sulfur content. This would add 20% to a plant's expenses, while building scrubbers could cost up to $200 million. At the Council on Environmental Quality, Bob Harris.
Dealing with the problem of acid rain is clearly a difficult one from the regulatory point of view. I think there are legitimate complaints that the federal government is not moving fast enough on this problem. From the point of view of it's one of these dilemmas of not knowing all the answers, but yet by the time we know all the answers, it will be too late because the damage will have occurred. And so it's inappropriate to wait until we have all the answers before we regulate.
California, the #1 agricultural state in the Union. Its success is based on irrigation. Too little rain falls in the major production areas which lie in the southern section of the state and the fertile but dry valleys between the coastal range and the Sierras. A large portion of the water which has made the desert bloom is imported from the Colorado River to the east and from the Sacramento River in Northern California. An elaborate system of state and federal projects sends the water along aqueducts to the heavily farmed and populated south. But in 1985, California will lose some of the water it gets from the Colorado River when Arizona completes its own Colorado project. Continued growth of farms and cities in Southern California will depend more and more on water from the north. That is the background for the hotly contested peripheral canal construction issue, which was recently approved by the California legislature after 15 years of north-south battles. The Delta is a 1,000-square-mile area of diked farmland and wildlife habitat formed by the confluence of the Sacramento and San Joaquin rivers before they flow into San Francisco Bay. Water from the Sacramento in the north is presently exported to Southern California only after passing through the Delta. The peripheral canal would bring Sacramento water directly to southbound aqueducts, bypassing the Delta completely. Delta farms and fisheries don't want to lose the natural flushing action of the Sacramento, which clears out salty water from irrigation and the San Francisco Bay. Northerners and some ecology groups feel the $600 million peripheral canal is a boondoggle for the growing urban population and large farming corporations in the South. Southerners and other conservationists would like to use northern water to replenish groundwater in the San Joaquin Valley. The agricultural boom there was created at the expense of drawing up water faster than it can be replaced naturally. Farmers there are afraid they may be running out altogether. Overpumping has also resulted in compacting of the soil. Compacted areas have lost forever their ability to store water. In some places, the San Joaquin Valley floor has dropped nearly 30 feet just since 1925. Water from northern rivers could alleviate the serious groundwater situation. In the Stanislaus River Canyon in Northern California, another water controversy rages. Abundant in wildlife, this limestone canyon is one of the few natural yet easily accessible wilderness areas left in the state. In springtime, the canyon walls are dotted with wildflowers. It is a magical place. One of its extraordinary beauties is the white water which roars through the canyon as the snowpack melts in the Sierras. Only 3 hours from San Francisco, these rapids attract thousands of rafters, including the less affluent and the handicapped, for whom this may be the only opportunity to experience a wild river. A river conservation study claims the Stanislaus is the most floated whitewater in the West and the second most popular wild river in North America. But the Stanislaus is on the front line of California's water wars. In 1978, the U.S. Army Corps of Engineers completed construction of the new Malones Dam, a 625-foot-high structure downstream of the Whitewater. It would create a reservoir of 800 billion gallons of water. Filling the reservoir to capacity would flood the 9 miles of Whitewater from the takeout point at Parrott's Ferry Bridge to the put-in point at Camp 9, completely destroying the rapids. The dam had originally been authorized by Congress for flood control in 1944. It would submerge and replace the old Malones Dam, whose reservoir held only 36.5 billion gallons. But appropriations to build it weren't authorized until the 1960s. At that time, the proposal was expanded to include water for power, fisheries and water quality control, municipal and industrial consumption, and irrigation, although specific customers were not designated. Opponents of filling the reservoir to capacity and destroying the canyon formed a group called Friends of the River. They contend that a smaller reservoir could control floods adequately. They point out that unlike state-funded projects, federal agencies did not assess the need for the water which would be stored, nor commit potential users to contracts before building the dam. Co-director of Friends of the River, Mark Dubois.
The National Environmental Policy Act was passed by Congress in the early 70s and required that everybody building a major dam or any other buildings had to file an environmental impact statement. And they did that on the Stanislaus River, and it turns out the Environmental Defense Fund found out that it wasn't adequate. So they sued the federal government, the Corps of Engineers, and said, you've got to make it adequate. Well, the courts said, yes, Environmental Defense Fund, you're right. It's inadequate, but we're going to give the Corps 6 months to make it adequate. So the Corps went back to the drawing boards and did some more paperwork and made the impact statement adequate. And the impact statement said, well, we're going to lose miles of incredible river canyon, we're going to lose all these caves, we're going to lose all these archaeological sites, all this biological habitat, but now we've said what we're going to do, now we can go ahead and build it. Many people have tried to say that the battle over New Malones Dam and the Stanislaus River is only a battle between the farmers and the rafters. And the rafters, of course, are only here to play and only to have fun. And the issue goes far deeper than that. I think, for one, it's hard to describe the magic of the Stanislaus River Canyon. But sometimes the laughing and the smiles you see on people's faces let you know how amazing this place is. And it touches people's spirits in a way that I've seen few places be able to do.
On the other side of the controversy is a group calling itself Friends of New Malones. John Hurtle, co-chairman of the association, has a dairy farm along the Stanislaus below the dam.
On our ranch, we milk approximately 450 Holstein milk cows, and then we have about 350 younger animals that we raise for replacement purposes. We raise about 1/3 of our forage needs, and the balance we have to purchase.
This year, Hurtle will have to lay out $10,000 for feed because his field was flooded. In order to save the canyon and the rapids during heavy rains and snowmelt season, water must be let out of the New Malones Reservoir. Both farmers and conservationists have agreed on a maximum release rate of 8,000 cubic feet per second. In the spring of 1980, less than half that amount was released. But even at that rate, riverside fields were flooded. John Hurtle.
I'm sitting in a field that is normally used to provide feed for our dairy cows. It went underwater this winter because of the heavy rains we had in California and the efforts that have been made to not store water in the New Malones Reservoir. The flooding that has occurred was preventable. The water that is standing here should really be saved for future use and not to continue to flood this field so that we can continue to farm it in the summer months. This, to us, is why we built New Malones.
This walnut orchard is the victim of indirect flooding. The trees are dying because their roots are soaked. Several weeks of constant releases from the dam caused the river level to be higher than the fields. The water seeps through the dikes. Long periods of pressure could cause the dikes to collapse, resulting in loss of the orchard. Friends of the river claim that farmers are greedy, cultivating down to the riverbank itself. Part of the authorization to build the dam required that loss of the wild canyon be compensated for by recovery of the downstream riverbank habitat. But farmers will sell their shore property to the government only if the reservoir is filled to capacity and the amount of water released downstream is reduced to even less than half the amount which was agreed upon. The battle over how much water the reservoir should contain is partially a battle of statistics and public relations. Each side has numbers to show why the fisheries would be healthier, how electricity could be generated and used more efficiently, how the stored water could best be used, how the environment would be served. The battle reached the U.S. Supreme Court, which ruled that the state of California could, within limitations, mandate the reservoir's capacity. California told the Corps it could not back water past Parrott's Ferry, the lower end of the 9 miles of white water.
In the spring of 1979, they finally started backing water up behind New Melones Dam. And as the water backed up, miles and miles of river started getting covered up. They were nearly coming to this point at Parrott's Ferry. And they were legally bound not to go above Parrott's Ferry, both because of historic preservation laws and legal memorandums they had signed, as well as because of a Supreme Court mandate. The State Water Resource Control Board back in 1973 had said that the federal government couldn't fill up New Melones Dam because they obviously didn't need the water for a long time, if ever, and the values of the canyon were so unique that they ought to hold the reservoir for a while. Well, the Corps was now getting ready to push above Parrott's Ferry, and they didn't really announce it. They just suddenly started telling their contractors to clear the trees around here. And when we got word of that, we got really excited. So some attorneys started trying to figure a way to force the Corps to legally stop doing it. And in the meantime, we started working with all the administrators that were forced to help the Corps abide by the other laws. But I had too often watched the Corps violate the integrity of the canyon. And each time when I thought I'd make a personal statement, each time instead I tried to work with the system. But each time the Corps' bulldozers moved faster than the administrative processes did. And so in the May of '79, when it was obvious the Corps was going to be up above Parrott's Ferry within a few days, I decided I needed to make a personal statement. And so I ended up attaching myself to a rock just downstream of here.
Dubois chained himself to a rock in a hidden place in the canyon. Neither rangers, the sheriff, nor the Corps could find him, despite a weak search by boat and helicopter. Newsmen, paddled in by night, reported that Dubois would drown if the filling weren't halted. The Corps opened the floodgates and stopped filling the reservoir. Dubois was unharmed. But Californians continue to fight over whether all available water should be tapped, especially for consumptive uses like agriculture, where the water is taken out of circulation. Head of California's Department of Water Resources, Ron Roby.
We have not tapped all the water resources in the state, nor should we. We have some very wonderful North Coast wild rivers that, in our opinion, should remain wild. Fortunately, development costs over there are expensive and the environmental problems are great. So there are some areas where there just shouldn't be development. Basically, a lot of the water is needed for in-stream uses of various kinds. And so while we have a lot that isn't dammed, we don't think that it's appropriate to just dam every stream in the state and to take every drop for consumptive uses.
Unlike California, Boston's water problem is less scarcity than cost. Many sections of the city are served by mains which need maintenance or have sprung hidden leaks as they lay underground for 100 years or more. 40% of the city's water is unaccounted for. As pumping and treatment costs rise, it seems economical to track down the lost gallons. Boston has one of the oldest water systems in the country, but other northeastern cities share the problem of old and leaking pipes. Checking the city section by section is the only way to detect these leaks. The Boston Water and Sewer Commission has stepped up its leak detection program. It employs pitometer associates who use a simple device which measures the flow in the mains, recording it on a photographic chart attached to a drum with a 24-hour rotation. The chart indicates what sections the commission should repair. The chart is interpreted by pedometer engineer Dave Liston.
We went into that house and put a piece of photographic paper on the drum, and then after 24 hours we'll take it off and develop it. We'll end up with a sheet like this. With this sheet, it's going to show us the rates of flow for the 24-hour period. You can see the rates of flow here between 2 and 3. 3 and 4 is steady. It's going to increase here 4 to 5, and then at 6, the dishes are being done, 6 to 7. Then it's interesting to look here, the peak flows we have right on the hours, 8 o'clock, 9 o'clock, 10 o'clock. There's a different age groups going to bed, brushing their teeth, washing up. And we come down here, and it's 11 o'clock. We get a high flow here between 11 and 11:30 with the parents going to bed. This is the time of day we're interested in right here, is the night flow, where there's steady usage, everybody is sleeping. And then we back up here in the morning, you can see 5:30 or 6 o'clock, people are getting up. 6 to 7 is a high flow, 7 to 8 is usually, 7 o'clock in the morning is usually the high flow of the day, and then back down after everybody's gone to work.
The hourly flows are then added, giving the total water consumption for 24 hours.
We'll take the night flow, compare that to the total consumption, we're going to end up with a ratio. If the ratio is 40 to 50%, that shows probable leakage in the section measured. This film in particular, we had a ratio of 70%, which showed considerable amount of leakage in this section that was measured.
Through this monitoring program, Boston has saved 4.5 million gallons of treated water a day. Such programs are costly, especially replacing buried pipes. The flow of federal tax dollars earmarked for water development seems to bypass this problem of America's older cities. At the Environmental Policy Center, Brent Blackwelder.
The National Wildlife Federation did a survey of water and power rates around the country. And what the shocking results of this survey were is that people in the Northeast are paying much more for water and power than people in the West. And yet, where does all the money to subsidize water and power go? It goes from the Northeast out to the South and the West, so that the people in the Northeast pay their own water bills, their own electricity bills, and then they also subsidize the bills for consumers of water and power in the West and in the South. That's an outrageous situation, and the only way it's going to stop is for people in the Northeast to insist that their members don't support that kind of pork barrel, and for them to insist that dramatic changes be made in the way federal dollars on water resources are spent.
Pork barrel politics in the scramble for funds for water projects is a major obstacle to a rational consideration of water policy by Congress. Increasing the water supply does not necessarily mean building expensive new projects. Non-structural alternatives could be explored first. Ron Roby.
The Department of Water Resources is looking toward conservation as the first thing you do to stretch your water supplies and looking for new supplies.
Agriculture consumes 85% of California's water. Savings made in this area through more efficient irrigation practices are of vital importance.
In addition, in agricultural conservation, we have a very aggressive program spending several $million a year on agricultural conservation methods. And one thing we're doing, we're trying time-of-day irrigating. We are developing with the University of California statistics and information to show farmers they can use less water for their crops. Conservation in some areas can bridge the gap between existing supplies and future needs.
Different kinds of irrigation systems and the water requirements of various crops are being studied at the University of California by Dr. Fala Aljaberry.
There are two principal types of irrigation: a gravity system, where one turns the water on the field from a ditch or from a river, and a pipe system. The pipe system, as example of that, is the sprinkler system and the drip system.
Sprinkler systems can be stationary or mobile. Some propel themselves across a field. They're fairly efficient, but do lose some water to evaporation. More efficient are drip systems. These bring water directly to the roots of a plant. None is wasted between the rows, and little is lost to evaporation. Both sprinkler and drip get their water from pumps, which can be activated for specific lengths of time and are often connected to automatic timers. Drip systems need to have their water filtered so that small particles will not clog up the nozzles. Fala Algebari.
In this area, we are studying comparative efficiency of furrow, drip, and sprinkler in pistachios, in almonds, and in citrus. We have found out that the drip system is more efficient. The sprinkler system comes next. However, sprinkler and drip irrigation are energy intensive when you compare them to gravity systems. The third system was the furrow. If the water that runs at the end of the furrow is collected in one corner of the field and recycled back with a very small pump to the beginning of the field, the efficiency of the system approaches that of the sprinkler, not quite. What determines the irrigation system is the type of the crop, the soil, the morphology of the land, the lay of the land. That determines a great deal what kind of irrigation system is feasible. Of course, it all has to be based on economics. We have concentrated our research in the past on drip and sprinkler systems. The energy was relatively inexpensive. Today, with the expense of energy, considerable effort is being made to improve the efficiency of gravity systems, which cover about 80% of the land in the state of California.
Leveling the field is one way to improve the efficiency of gravity systems. It's not a new idea, but improved machinery makes it easier to scrape off the high spots and fill in the hollows. If the land is leveled along a gradient, the flow of water can be controlled. The greatest efficiency can be achieved by dead leveling, because once the water is pumped onto the field, it doesn't flow at all, but sinks into the soil and is absorbed by the plants. Dead leveling has become possible with the help of laser beams. A flashing laser set at a certain height rotates around the field 5 times a second, creating a plane of light. A photosensitive receiver on top of the earth-moving machinery intercepts the beam. The signal is transmitted to the hydraulic system, which automatically adjusts the scraper blade. The field can be leveled to any grade the farmer wants by tilting the laser beam. Leveling his field with this sophisticated equipment can cost a farmer as much as $350 an acre, but it is a one-time expense. It repays itself because a dead level field can reduce the water needed for irrigation by 30%, while simultaneously increasing crop yield because all plants will receive the same amount of water.
That has proven to us through our experimentation of being very efficient, whereby we can turn a high head of water to a specified depth and flows all the way to the other end, and no one part of the field will get more than the other. The efficiency of this has been measured of being better than 90%, which approaches that of the sprinkler system, yet with lower energy.
Another experiment in irrigation is the traveling trickle irrigation system. This combines the benefits of the drip system with the mobility of some sprinklers. As it moves along the rows, nozzles drip controlled amounts of water drawn from a central channel which runs the length of the field. The nozzles are connected to a long arm planned to reach half a mile on each side of the channel. Again, lasers are used to keep the sections in line. The power for this system will eventually be replaced by solar energy. Although home use accounts for only 6% of the water we use, savings there have been vigorously encouraged in water-short areas. The drought of the mid-70s in California could have been a disaster when reservoirs dried up, but citizens made every drop of water count. Ron Roby.
The thing we learned from the drought is people can use less water and survive. In Marin County, which was the most celebrated area, they cut back more than half, and they did have lifestyle changes. But we have found that people can reduce 15 to 25% without a significant lifestyle change, and we think they can cut back 15% without any change at all. That's something that we expect. And so we are now planning in times of drought to simply use less water. It was always assumed by water planners that in a dry year, you would have to have as much water as you have in a wet year. And so we, in effect, overbuilt.
The Irvine Ranch community south of Los Angeles was built with recycling in mind. Lawns fronting all the homes and public recreation areas are watered by automatically controlled sprinkling systems run by the municipality. The water comes from the city's sewage treatment plant. What the town doesn't use goes to the Irvine Ranch Company for agriculture. At nearby Water Factory 21, an advanced sewage treatment plant near the Pacific Ocean, another recycling experiment is going on. Highly treated water is pumped down into the 4 natural underground reservoirs, or aquifers, from which Orange County draws its drinking water. The treated water acts as a barrier against salt water from the ocean, which seeps into the aquifers when the fresh water table is drawn down too far through overpumping. This is a problem which plagues many American coastal cities dependent on groundwater. Not enough is known about the way the water moves in these aquifers, but it seems likely that after 3 months, the recharge water is drawn up for consumption. This is the closest we have come so far to drinking treated sewage water on purpose. As pristine waters become less available to us, will we be drinking treated sewage water in the future? Bob Harris.
In the United States, in the future, we will have to recycle sewage for drinking purposes. But I think it's important to remember that communities right now are drinking treated sewage all over this country. Let's take the Mississippi River, for example. New Orleans is at the end of the Mississippi River. Memphis and St. Louis and Baton Rouge, not too far north of Mississippi, use the water, discharge their sewage into the water, and then New Orleanians use the water, the Mississippi River, for drinking purposes. So this is recycling of sewage effluent for drinking purposes. Inadvertent, if you will.
Inadvertent recycling of sewage, however, is not without risks to both those who drink it and the creatures which live in it. It has been known since 1972 that the mixture of chemicals found in New Orleans drinking water could increase the risk of cancer. Bob Harris worked on some of the New Orleans studies.
Disclosures in New Orleans regarding cancer-causing chemicals in drinking water was really the first battleground when drinking water and water pollution problems came face-to-face with public health problems in this country. I participated while I was at the Environmental Defense Fund in a study that looked at cancer rates in Louisiana and their relationship to drinking water quality. And we found a strong association between cancer at certain sites, primarily gastrointestinal organs and urinary tract organs, and drinking water from the Mississippi River. Those communities that got water from the Mississippi River had higher cancer rates at those sites.
One of the carcinogenic substances found in the New Orleans drinking water was chloroform. The Environmental Protection Agency lab in Cincinnati looked into this and found something alarming, which corroborated a recent Dutch finding.
They were investigating why chloroform was in drinking water because they had found chloroform in New Orleans. And lo and behold, they found that the water coming out of drinking water treatment plants had more chloroform than the water coming into the drinking water treatment plants. And of course, that led to, together with this just published study from the Netherlands, to the unmistakable conclusion that something was going on in the drinking water treatment plant. It was later found that adding chlorine in the disinfection process, which every drinking water treatment plant in the United States does, practically, produces chloroform and a whole variety of other chlorinated organic chemicals. A class called trihalomethanes is a class that EPA has just now regulated. There are a class of chemicals that, there are 4 chemicals, and they all cause either mutations or cancer in laboratory studies.
As a result of the New Orleans findings, Congress dusted off the Safe Drinking Water Act and gave the EPA funds to test drinking water around the country.
The EPA immediately after the disclosures in New Orleans, launched into a nationwide survey of both surface water, polluted river water, and groundwater supplies. And they found that the contaminants that they observed were present in New Orleans were ubiquitous in the nation's drinking water supplies. Almost all surface water supplies, except for a very few, were contaminated with these types of chemicals.
So we had a double-barreled problem. Man-made chemicals dumped into our surface waters and trihalomethanes formed from chlorinating natural organic chemicals. These could come from the effluent from our sewage treatment plants, or from agricultural debris washed into the rivers, or from the runoff from feedlots, or from decayed forest debris and marshes. These non-point sources contribute huge amounts of organic chemicals to our waters and are nearly impossible to control. The ubiquitous nature of organic chemicals points to a potential trihalomethane problem for every surface water supply treated with chlorine. Bob Harris.
The biggest problem in encouraging that water treatment companies reduce their problem from chlorine is convincing them that there is a problem to begin with, that there is a health threat associated with the use of chlorine. By not chlorinating water as it first comes into the drinking water treatment plant, but waiting until the end of the drinking water treatment plant, will reduce the trihalomethane and the unknown fraction simultaneously to over half of their former levels.
It took the EPA 6 years from the discovery of this problem to rule on safe levels and require treatment plants to make necessary changes in their treatment process. Even then, the rulings affect only facilities serving more than 10,000 people. Assistant Administrator of EPA's Water and Waste Management Division, Chris Beck.
And it takes us a number of years to develop the data, to develop the precision in terms of facts and details in terms of approaches that need to be employed before, in fact, action can occur. And even after we've made certain determinations, federal law in all instances require that we go out, give public notice, hear comments, get data, evaluate what we've learned. And one of the things that we found is very difficult for us as an agency, because we are on the frontier of knowledge with regard to many chemicals, is beginning to get data about at what levels the human organism begins to have effect. We have to do studies. We have to gather information to make those determinations, because those determinations not only are for the purposes of protecting people's safety, but when this agency picks a number, determines that that's what's important, behind it are tremendous costs. Their economic costs, their social costs, their behavioral costs. And we've come to learn that it takes time to do this.
Despite the time it takes to determine and regulate them, there's no assurance that legislated levels are really safe. Toxicologist Rudy Yeager.
There seem to be no accepted ways to determine safe levels for carcinogenic chemicals. It would seem better to say that there are ways of deciding what might be acceptable risk. That's a governmental process, a governmental job. And then after it is known that a risk exists, it's up to the public to decide whether the risk is acceptable. With public water supplies, you don't really have a lot of choice. You either drink bottled water or you don't drink the water. You find out why the contamination was there, you try to clean it up, you engage in the democratic process. But the final solution seems to be the water supply should be clean and pure. And the way things are going, it doesn't seem like it's getting cleaner or purer. I think it's hard to know what is a safe level, and I'm speaking as a professional. I can't guarantee it. I can give you some numbers. 1 in a million, 1 in 500,000. It may be that the government is using 1 in 500,000 as their level of acceptable risk. I would think that's okay as long as I'm not the one.
I think that there's been a public perception that water is a plentiful resource and completely renewable. One of the things that I think has been very much part of a misunderstanding with regard to water resource is the awareness of how many things that we've done to interfere with our groundwater.
Stand by! Fire!
Bedford is one of 22 Massachusetts towns plagued by groundwater contamination. Proud of its revolutionary history, Bedford's stubborn Yankee spirit is not merely a thing of the past. With a town meeting form of government headed by selectmen, the town is determined to solve its water problems. It was by chance that Bedford discovered it had a water problem. Dan Oblas, a physicist who lives in town, brought a sample of Bedford water to a colleague he worked with at the GTE lab in neighboring Waltham. Don Duggar was designing new procedures for in-house use for finding trace organics in water by using activated charcoal. He did the analysis by gas chromatograph and mass spectrometer. This combination of equipment produces a specific fingerprint of the chemical being analyzed. A gas chromatograph alone would not produce this fingerprint. Dan Oblas.
The first analysis that Don Duggar looked at happened to be water from the laboratory fountain. Our water in Waltham comes from the MDC, Metropolitan District Commission. It's well known that water is of high quality, and so he did not see any organics in the water. Subsequent to that, we decided we needed a dirty sample of water, and I volunteered Vinebrook.
Oblas was curious about Vinebrook water, which runs through his property.
The real estate agent told us when we first moved in that we had fish in our brook. When we came here, there weren't any fish. I guess the question we asked was how good or how bad was the water? Indeed, there were very low concentrations of organics in Vinebrook. After Vinebrook, we decided that maybe we should look at some of our tap water, and we looked at the tap water from my residence, and we were quite surprised to find out there were very high concentrations of dioxane and tetrahydrofuran, and lower concentrations of other halohydrocarbons. At that point, we decided that it was possible that what we were seeing was not a real effect, but something which was just transient, something which just occurred once and would not appear again.
So for 3 more months, they sampled water sources as well as the tap water. 8 wells drawing from 3 aquifers supply the town with all its water. The Shawsheen River partially recharges 3 of the wells. The Shawsheen, in turn, is fed in part by the Beaver Brook wetland. All of these sources had consistent chemical contamination, particularly from trichloroethylene, tetrahydrofuran, and dioxane. Dan Oblas.
It became apparent that one would have to be concerned about the toxicity of these materials, and so we went to the literature to find out how bad they were. And dioxane is not on the priority pollutant list, so one could not find it that way. After making a number of telephone calls and inquiries, we finally were led to Dr. Yeager at Harvard Medical School, and when I related the story to him about the high levels of dioxane, he was concerned.
The level Oblas was finding was 1,000 parts per billion. Yeager's concern was that it was there at all. Rudy Yeager.
I happen to know about dioxane as a toxic chemical because I had recently attended the Society of Toxicology meeting at which the Dow Chemical Company had confirmed an earlier report which suggested that high concentrations of dioxane in the drinking water were carcinogenic to rats. The tests that were done by the Dow Chemical Company looked at the carcinogenicity of dioxane at 1%, 0.1%, and 0.01% in the drinking water, which are substantially above the levels found in Bedford. As far as I was concerned, even though I knew that the levels in the drinking water were well below what seemed to be a no-effect level in the Dow study, I wasn't satisfied with that, and I advised him not to drink the water.
Once we found out that the levels of dioxane and tetrahydrofuran were for real, as they kept repeating for 3 months, and after conversations with Dr. Yeager at Harvard, it was apparent that we had to notify the town. And the problem was, how do you notify the town without alarming the populace?
What Oblas decided to do was to present the information to the town selectman, Bob Fulweiler.
Our honorary commander-in-chief.
When Dan Oblas notified us that there were chemicals in our water supply that were worthy of concern, one of our first concerns was, who was Dan Oblas? We didn't know. Was he for real or not? So we spent a day or two, finding out whether he was in the field he represented himself in. Indeed, he was. And so at that point, we started doing an independent investigation of the potential toxicology and got some evidence that corroborated his evidence that some of the chemicals were indeed toxic. We turned off the supply from the wells that were known to be contaminated at that point.
Closing the wells meant that Bedford lost 75% of its water supply. Townspeople began wondering if in the future terrible diseases would beset their children because they drank contaminated water during their formative years. In the meantime, the selectmen arranged to buy water from neighboring towns.
Unfortunately, all these arrangements, having lost some 75% of our indigenous supply, has cost us a lot more. It costs the town now about between 2 and 2.5 times what it cost prior to the closing of the wells, because the water does come out of the ground as is. All we have to do is pay for pumping, whereas when we purchase from the other towns, we pay retail rates the same as their local residents do.
There was, in addition, another problem which appeared, and that was it was apparent that these materials, which are degreasing agents and solvents for industrial and commercial applications, that were here because of industrial or waste pollution. Did they come from the local area? Or are they still coming from the local area? And the question was, who's doing it if they are? And do they know they're doing it?
The town hired an engineering firm to track down the sources of contamination. Test wells were sunk all over town, and samples were taken from municipal sewers at the points where specific companies discharge their effluent. The consistently high levels of dioxane in the Beaver Brook wetland were traced to a company bordering the marsh. The town is now suing the companies suspected of releasing chemicals to recover rehabilitation costs. Bob Fulweiler.
Recovery of the wells is being paid for entirely by the town of Bedford at the present time. We have appropriated $75,000 at annual town meeting this year, which is going to go toward recovering, hopefully, this well and perhaps the next well. And beyond that, I assume there will be additional expense if we want to expedite recovery. Unfortunately, Bedford finds itself on the forefront of this problem. One of the communities in Massachusetts to first discover a chemical contamination problem, and we felt that the town of Bedford had to do it on its own because there just weren't any viable sources of funding outside of the town's government itself.
What happened in Bedford is becoming less unusual. As state laboratories and other governmental agencies start getting sophisticated equipment like gas chromatographs and mass spectrometers, they're beginning to find things that they never found before. Dioxane in Bedford's drinking water is now being replaced by a variety of other chlorinated and non-chlorinated compounds being found in a number of drinking water supplies. Water is no longer considered pure by bacteriological analysis, but now needs to have this sophisticated GC mass spectral fingerprint done on it.
Pure water and cheap energy have been the foundation of our country's prosperity. The energy crisis taught us that in the long run, wastefulness carries a big price tag. Do we need a water crisis before we begin to manage our resources wisely? Chris Beck.
Right now, many problems are occurring in the environment, and the people who are bearing the brunt of it are the people's who have it in their backyard.
Brent Blackwelder.
Congressmen all over the country are so eager to get a project for their districts that they never consider anything such as a priority listing of needs.
Bob Harris.
There is foot dragging, but it's a dilemma. And there's always foot dragging when we don't have all the answers and when the costs are high.
Mark Dubois.
I've been learning enough about the dam battle for so many years and about the river that, for one, I knew that we can have both. I knew that we can have the life and the magic of this beautiful place that's all around us, and also have power and water and needs that we need in urban areas. And it's not an either-or. And I knew that we were getting ready to destroy this place, not because we needed to, but only because we didn't want to take responsibility and use what we have more wisely.
Today's water issues are complex. Solutions are difficult, but not impossible. The question is not whether we can clean up contaminated water sources or filter chemicals out of drinking water or prevent acid rain or leave some rivers wild. The question is, how much are we willing to pay to do these things? On what basis will we make our choices? Who will decide? Industry? Individuals? Elected officials? We have neither more nor less water than our ancestors did. Will our children be able to use it?
The material on this video cassette is protected by copyright. It is for private use only, and any other use, including copying, reproducing, or performance in public, in whole or in part, is prohibited by law.